All right, so I just want to, okay, so we covered sampling distributions, and a sampling distribution, the idea behind the central limit theorem is that when we take a sample and we look at the mean of the sample, what can we say about the mean of the sample?
It's the same as the population?
No. So if I take a random sample from a population, I don't know what the mean of this random sample is going to be, but what can I say about it?
It'll follow a normal distribution.
It comes from a normal distribution, okay? As long as those conditions are met. And what were those conditions?
Sample's not too big or too small.
Okay, the sample's not too big or too small, and then the other key one
They're random.
is that the sample is selected randomly, right? So if we've selected a sample randomly, and it's not too big or too small, then the mean of that sample comes from the normal distribution, okay? So we can use that basic, that premise, or that fact, we use that as the basis for pretty much what we're going to do from here on out, okay? Pretty much, okay? A few things are a little bit different, but we're basing our next thing, which is our first introduction to inference, based on what we understand about samples and sampling distributions. Yes?
Why, if we have a finite population, are we not doing a finite population correction factor?
Finite population
This
correction.
thing.
Let me see, I don't know if I fully understand.
Like if you do replacement, it says you don't need to because there's an infinite number, but if you don't do
Okay.
it,
Yeah, alright.
not to make it any more difficult.
Yeah, okay. So the questions about this finite population correction factor, that is, we kind of take care of that by saying, make sure your sample is not too big,
Okay, I gotcha.
okay? By making sure our sample is not more than 10% of the population, that finite population correction factor is pretty much close to 1.
Okay.
It's not a big deal. But if you're taking a sample much bigger than that, then you should use that finite population correction factor. I would just say don't take a sample too big, okay? But that's rarely a problem. Okay, but so we understand something about the y-bars. We know that y-bars come from a normal distribution, and we're going to use that as kind of the foundation for where we're going with inference. Okay, so our first introduction to inference is going to be confidence intervals. So this is now chapter 6. And the idea is this, okay? So when we talked about sampling distributions, I said, we know the population is this. Like, we know the population of IQs is normal with mean 100 and standard deviation 16. And, what's the probability that a sample of 8 people has an average IQ of 108 or higher, or something like that, okay? So we can... But how do I know that the mean of the population is 100 and the standard deviation is 16?
Making an assumption.
Yeah, well, the fact is I don't, okay? I just kind of said that in this problem, okay? But when we're dealing with real life, we have no idea what the population looks like. What's the average height of men in the United States? What's the true average height of men in the United States? Do we know? No, we have an idea. It's around 5'9", 5'10", something around there. But the only way to get the true average height would be if somehow I was able to freeze time right now, gather all, 150 million men in the United States, have them stand up, and we measure their height, and then I add up the heights of all 150 million people, divide by 150 million, and then I get an average, right? That's the only way I could get the true average or true mean height in the population. Okay. So the population mean, in most cases, is unknown to us. Population mean is usually unknown, okay? We generally don't know what mu is. But how did I come up, I said, what's the population mean height? What's the mean height of men in the United States? And I said, somewhere between 5'9" and 5'10". Now, how did I even come up with those numbers?
From a sample or from multiple samples?
Yeah,
Within the
okay.
state?
So, well, basically I just read something on the internet, but how did the internet get this number, right? Well, based on we can take a sample. So to kind of, maybe we want to say something about the population mean, okay? Let's say we want to know what the population mean is. We want to know what the population mean is. So we take a sample. Okay. And maybe I take a sample of 30 men. And we measure their heights. Okay. Let's say the y bar of these 30 men that I measure the heights of. Let's say the average height here is 59.7, so 69.7 inches. What does this tell us about the population mean? So the average height of 30 men that I selected randomly, so I need to say take a sample randomly, not a trivial detail actually. So I take a sample of 30 men at random, and we measure their heights, and the average of these 30 men is 69.7. What does this tell us about the population?
It's an estimate of it.
Okay, this serves as an estimate of the population mean, okay? But is the population mean necessarily 69.7 inches?
No.
No, okay? We still don't really know what the population mean is. Okay, so let's put that thought in our mind, and but we'll put it on hold. And now I'm going to tell you a story, or make up a story, something. All right. Okay, so let's say somebody posts this on Instagram. Here's a picture. All right, and what it's a picture of is what is this a picture of?
Football field. What?
This is a
Dog.
dog. All right, it's a dog on a football field, okay? But it's not just a picture of a dog on a football field, okay? It's a picture of a dog going for a walk on a football field with its invisible owner and invisible leash, okay? So this is a picture of a dog on a football field with his invisible owner. Owner and invisible leash. So here, there he is. Okay, so we've taken this picture. Now, where's the owner?
We don't know.
We don't know. We don't know. Okay? But the owner can't be too far away from the dog, right? Or the dog shouldn't be too far away from the owner because he's on a leash, right? So unless this leash is, if the leash is not really long, then we know that the owner has to be somewhere near the dog, okay? Because the dog can't stray too far from the owner. All right, I'm going to tell you that the leash is elastic, okay? It's invisible, but it's the leash is elastic. And our dog will put some pressure on the leash, but he doesn't like to strain too hard, okay? And the dog will sometimes strain, but not often. Against the leash, but not often. Okay, and we've studied the behaviors of the dog well enough to know that about 68% of the time, okay, the dog remains within 1 yard of the owner. And then 95% of the time, the dog remains within 2 yards, or 1.96 yards of the owner. And 99.7% of the time, what? The dog is within 3 yards of the owner. Okay, so in our picture, the dog is at the 50-yard line. So where is the owner?
Most likely within 47 and 53.
Okay, so there's a few things we can say, okay? I can say, all right, you know what? I don't know exactly where the owner is. But because of what I know about the behavior of the dog and the leash, I can say, so I'll just, but, because I understand the behavior of the dog, I can say something like this. So I don't know exactly where the owner is, but I am 95% confident that the owner is between the 48-yard line and 52-yard line. Does that make sense? Okay? Or I could also, and I can say I'm 99.7% confident that the owner is between the, 47-yard line and 53-yard line. Technically there's hyphens because the number is an adjective. Okay. Do these statements make sense? Now, is it possible that the owner is actually at 46.5, 46 and a half.
Sure.
Yeah.
Yeah, it's possible,
Okay.
but we would be surprised, because that means the dog really is straining hard against the leash, or more than what we would normally expect, right? Okay? You know, I could even lower my confidence and say I'm 68% confident that the owner is between the 49-yard and 51-yard line, okay? So again, in all of these situations, I don't know exactly where the owner is, but because I know the dog's on a leash, and I observe the dog right here, I know that the owner can't be too far away. Okay? Does that make sense? Okay, so we're going to use that same idea, okay? But the dog is our Y bar, okay? This is what we observe. And the location of the owner is our mu, okay? Location of invisible owner is our population mean mu. Okay. And from what we studied earlier today with sampling distributions, we know that the behavior of Y bar follows the normal distribution, meaning 68% of the time it's within one standard deviation of the population mean mu, right? And what is that standard deviation? It's actually the population standard deviation sigma over the square root of n, right? And we also know that because it follows the normal distribution, 95% of the time, Y bar is going to be within 2 times sigma over the square root of n of the population mean mu, right? Is that okay? All right, so so again, in this situation, our population is unknown. We don't know, the population mean is unknown. We don't know the location of mu. That's like our invisible owner. But we've taken a sample, and from the sample we observed Y bar, okay? And Y bar is what we can observe, and we know where Y bar is located, and we know that Y bar will not be too far away from the population mean mu. I mean, it could be, but that would be one of those rare cases when we're not expecting it to happen, but it did. Okay. So let me put this in more confidence intervals. Okay. Okay, so likewise, Y bar, which is known, visible, comes from a normal distribution centered at mu with standard deviation equal to sigma over the square root of n. Okay. So likewise, so we can also say statements, so we can make statements like, I am 95% confident that mu is between, what would I put as my boundaries for where mu might be? Yeah. So here I came up with, I'm 95% confident that the owner is between the 48-yard line and 52-yard line. Now, how did I come up with those numbers? And how can I put that here? So I'm 95% confident that mu is between
28.
I'm going to do y bar minus 2 times sigma over the square root of n. Does that make sense? And what's the other side going to be? Y bar plus 2 times sigma over the square root of n, right? This is how I came up with the 48 and 52 and the 47 and 53. Basically, I'm taking what I know, my y bar, and I'm going down 2 standard deviations and going up 2 standard deviations. Okay, is that all right? Okay. Now, notice I'm using the word confident. Why would I not write there's a 95% probability that the owner is between 48-yard line and 52-yard line? Why wouldn't I write there's a 95% probability that mu is between here and here?
Because there's a chance that, like in our example, the leash breaks, and so the owner is in another city or something.
I'm sorry?
Basically.
No, that's not what we're saying here. Okay, this is the frequentist notion of probability that we live by. Okay, so just put this on hold. All right, I have a coin. Okay, what's the probability that it lands on heads?
0.5.
0.5. Great. Okay. Okay. Now I'm going to ask you this question again. Okay. What's the probability that this coin is on heads?
0.5.
Hang on. Let me just ask you that question again. What's the probability that the coin is on heads? Okay, and this is where we get into trouble, okay? So before I flipped the coin, it made sense to ask a question of probability, okay? But here, the coin has landed. It doesn't make sense to ask a question of probability anymore. It has happened. There's no probability anymore about it. It either is heads or it's tails. So it doesn't make sense to say that there's a probability of 0.5 that the coin is heads. Yeah, I mean, you guys don't know, but I know the answer, right? So all you guys can say at this point is I am 50% confident that the coin is heads, okay? But to say that there's a 50% probability that the coin has landed heads doesn't work, okay? Because the coin has landed. There's no probability. There's nothing, I don't know, unknown about it, okay? It landed heads, by the way. And so here, when we're dealing with this, okay, the location of the owner is fixed. It's set, okay? It doesn't make sense to talk about there's a probability of the location of the owner or the probability of the population mean, okay? It doesn't make sense to say that there's a 95% probability that the mean is between these two values. It either is in this value range or it's not, okay? There's no mystery about it. We don't know whether it is or not. We don't know. But it's set, okay? The coin has landed. You guys don't know how the coin has landed, but it's set. It doesn't make sense to talk about a probability here, okay? And just like that, right here, it doesn't make sense to say there's a probability about mu. It's set, okay? So all we can say is we can just talk about a degree of confidence, okay? And that's why they're called confidence intervals. If you subscribe to the other view of probability, then it becomes a probability interval. But here, with this viewpoint, it's fixed. We can only talk about confidence here. Okay, does that work for everyone? Okay, there is still a problem with this. Okay, so far, is everyone okay with how we ended up with y bar minus 2 times sigma over the square root of n, and y bar plus 2 times sigma over the square root of n. Everyone's okay with that? Okay, there's still a problem here. Can you guys see the problem?
Errors.
Huh?
Possibility of errors.
Okay, well, I'm not sure what you mean by possibility of error. Okay, why did we do this? We're coming up with this because we want to understand something about mu, the population mean, right? We don't know what the population mean is. Okay? At the same time, if we don't know the population mean, do you think we'll know the population standard deviation? Probably not, okay? I'm trying to think of a situation where you happen to know the population standard deviation, sigma, but you don't know the population mean, mu, okay? And I can't think of any off the top of my head other than some contrived example where, I don't know, you've got some robot in the lab that's behaving a certain way, but somebody has tampered with it, and you don't know, I don't know, okay. I can't think of any, like, real life situations where, you know, sigma is known, but mu is unknown, okay? And technically it's not 2, it's 1.96, right? Because as we look at, let's, here, I guess before I get into this whole issue with sigma known or unknown, and in 99 out of 100 cases, sigma will be unknown. Let's just deal with where this 2 came from, or technically 1.96. So if I want to be 95% confident about something, let's think of our normal distribution. I'm going to put, if I put 95% in the middle here, how much do I have in each tail?
0.25. 2.5.
2.5%, so I got 0.025 over here, and 0.025 over here. And so if you look in your z-table for what gives you 0.025, the number you get is negative 1.96 and positive 1.96. Okay? So what would I use if I wanted to make a 90% confidence interval? If I wouldn't use 1.96. You might want to look in your table if you've got a chance. What would I use for a 90% confidence interval?
1.28?
Not 1.28. 1.28 would be for an 80%.
Um, 1.28.
No, not 1.28, not 1.29.
1.64.
1.64, 1.65. Okay? I'm going to split the difference and do 1.645. Okay? 1.64 or 1.65. Plus or minus. Why?
Y plus or minus?
Oh, no. Why is it 1.645 and not 1.28? Well, if you look at the negative side, you're looking at the side that gives you 0.05. Okay? When you looked up 90% in your table, okay, you have to remember you want the middle 90%. So really, if I shaded all the way from over here all the way up to here, I would be looking for 95%. Does that make sense? Mm-hmm. So I would have 95% to the left of 1.645 and 5% beyond it. Okay? No? Confused? Alright, so for 1.645, so this is, I am 90% confident that mu is between basically y bar plus or minus 1.645 times sigma over the square root of n. Okay? Or is within y bar plus or minus. Okay? Good? Is this okay? Does that make sense? Okay, so that's how we get these different values here. But again, I'm telling you there's a problem because we don't know what sigma is. Okay, we don't know the population standard deviation sigma. So we have to deal with, well, so what do? I have no idea what the population standard deviation is. So what should I do?
T.
Huh?
T. Never mind.
T? What? Well, we're going to end up using the T distribution, you're right. But so I've taken a sample. So I guess the previous problem or whatever situation I made up was we took a sample of 30 people, 30 men, and I calculated that the average height of these 30 men is 69.7 inches. Okay, so that's our mean. So I've got my y bar, but I don't have sigma. Okay, I've got a square root of n also. I've got an n, so I can do square root of n, no problem. So what should I use instead of sigma? Just make up numbers? What do I do? Is there anything I can do? Alright, well I'll tell you what we're going to do. I'm going to use my sample standard deviation as a guess for the population standard deviation. Okay, I'm going to use S, which is the standard deviation from my sample, as an estimate sigma. Okay, does that sound fair? So I don't know the standard deviation of the population, but here I've taken a sample of 30 men, and I can calculate the standard deviation of these 30 people, and maybe I get 3.1 inches. So let's say S is equal to 3.1 inches. Okay. Can I use that as an estimate for sigma? Does that seem okay? All right. Does anything feel uneasy about this, or are we just good? Yeah.
I would like to know why you can.
Yeah.
do
Well,
that.
so the short answer is, we can, but we have to take this into account. Okay. This is not really sigma, right? This might be bigger than sigma. It might be smaller than sigma. Okay. We don't know. I mean, just like y bar isn't necessarily equal to mu, it might be bigger or smaller than mu, we have to take into account that S might be bigger or smaller than sigma, okay? And here I'm trying to make a confidence interval for where mu lies, okay? So let's just think back to this example with the dog and the owner, okay? And I told you, okay, so the leash is elastic and the dog doesn't like to stretch too hard. So 95% of the time, the dog is within 2 yards of the owner. And then I'm like, oh wait, no, I can't remember. Maybe the leash is tighter than that or looser than that. So maybe the dog doesn't mind going a little bit further than 2 yards, or maybe it was that the dog didn't like to go more than 1.9 yards or something, okay? What if I say, bring in this kind of this uncertainty about the leash itself? Now, if you want to be 95% confident about where the owner was, okay, where would you say the owner is? So before we said the owner's in between the 48-yard line and 52-yard line. What would I say now? I'm 95% confident that the owner is
somewhere between those estimates or errors?
Yeah, but I mean, should I make this, so before I said, I gave myself basically a 2-yard cushion from where the dog was, right? So the dog is at the 50-yard line, and I said the owner's probably within 2 yards of the dog, because I understood how this leash worked. But now I'm like, I can't remember if this leash was actually either looser or stronger or something. Okay, so if we wanted to be more confident, equally confident, 95%, now that I'm uncertain about the leash, should I say the owner's within more than 2 yards or less than 2 yards of the dog? What should I say?
More.
A little bit more, right? Because of this extra uncertainty introduced by not knowing how much this leash actually stretches, I should kind of give myself some cushion here about where the owner is, and I'm going to say, maybe I better say something like 2.2 yards of the dog or something like that. Okay, I mean, that's an arbitrary number. Well, we're going to do the same thing here. Because I'm using S rather than sigma, using S introduces another layer of uncertainty. Okay, using S in the place of sigma, some extra uncertainty. Okay, so we're going to compensate for that. So rather than using 1.96 for the 95% interval, or 2, we're going to use a number a little bigger than 1.96, okay? Okay, so when we used sigma, we said we are 95% confident that mu is within 1.96, or essentially 2 standard deviation over n of y bar. Okay? So rather than 1.96, we're going to use a bigger number. Okay? So how much of a bigger number do we need? Well, this all depends. Okay. Okay, so I have a sample of 30 men, and I got the standard deviation to be 3.1. Do you think that's a good estimate of sigma or a bad estimate of sigma?
How could we know?
All you know is that it's come from, yeah, well, how could we know? Okay, well, let's say I took another sample. This time I took a sample of 300 men, and the standard deviation was 3.2. Okay? Which one do you think is a better estimate?
3.2.
The one that's come from the sample of 30, or the one that's come from a sample of 300?
300.
The one with 300 people, right? We took a larger sample. We feel that this is going to provide a better estimate than the one from the smaller sample. Okay? So that is also taken into account with how much of a bigger number we're going to use. If our sample is small, we're going to compensate by using a much bigger number than 1.96. And if our sample is really large, we compensate by using just a number that's a little bit bigger than 1.96. Okay. much bigger because everything is relative. And then if the sample is huge, R number only needs to be a little bigger. Than 1.96. Okay? So this leads us to the t distribution. Okay? So we use the t distribution. Okay, the t distribution looks a lot like the normal distribution, except it's a little bit wider. Okay? And it depends on something called degrees of freedom. So let's say this is my normal distribution. Okay? I'm going to draw a grossly exaggerated version of the t distribution. It's actually not going to be this much different. Okay, this would then be the t distribution with maybe some degrees of freedom. Okay, this is the t distribution. So it looks like the normal distribution, but it's just kind of stretched out. Okay, and you can find this in your book. Table 4, page 618. If you have the hardcover, it's inside back cover of the book. Okay, and you'll see the t distribution laid out in something else. Okay, it looks different from the normal distribution. Okay, and the t distribution also takes into account degrees of freedom. So you have basically the t distribution for a one size sample might look like this, and then you might have another t distribution that looks like this. Okay, so this would be a t distribution for a large sample where it's not as stretched out and it looks more like the normal distribution, and then you have a t distribution for a small sample where it's more stretched out. Okay, I don't know if this makes sense. And we'll talk about the t-table here. And so if you have a t distribution with infinity degrees of freedom, meaning you're basically taking a sample of size infinity, what should that look like?
Is it normal?
Yeah, so t distribution with infinity degrees of freedom becomes the normal distribution. So a t distribution with infinity degrees of freedom is the normal distribution. Okay, and then a t distribution with fewer degrees of freedom is more stretched out. Okay. And the concept of degrees of freedom, it's a tough concept. Well, degrees of freedom, or abbreviated DF, for us is going to be calculated as the sample size minus 1. Okay? So if you take a sample of size 5, you have 4 degrees of freedom. And if you take a sample of size 300, you've got 299 degrees of freedom. And you don't have to write this down, but the concept of degrees of freedom comes from this. So let's say we're going to play a game, all right? We're going to have, I'm going to say, okay, somebody tell me what the, we're going to pick 5 numbers here, and let's say we want to make the average of those 5 numbers to equal 10, okay? I can let you guys pick the first 4 numbers, and as long as I get to pick the last number, you guys can pick any set of numbers, and I can make sure that the average of those 5 numbers is equal to 10, right? You guys pick any 4, and I just have to make sure that when you add them up, it adds up to 50, basically, right? So basically, you guys are free to pick 4, and the last one is locked. Okay, so that's where this idea of degrees of freedom equals n minus 1 comes from. Well, anyway, let's take a look at the t distribution, or this t table, okay? And I don't know, this is a little archaic. We all do things with computers now, but I guess we're going to learn things using the table, and that's how you guys will be tested. Okay. Page 618 in the book. 618, and it looks like this. Okay, so if you look at that bottom row with infinity degrees of freedom, okay, you're going to see some familiar numbers here. And so let's look at the bottom row and the top row. Okay, so the top row starts off with 0.20. These are actually the column headings. And let's look over to the column heading 0.05, and then also the column heading for 0.025. Okay. So the way this works says if this is the t distribution with infinity degrees of freedom, which is actually the normal distribution, and I go to the column heading 0.05, what number do I find there? 1.645. Okay? I hope this looks kind of familiar. And that means if I draw a line right there at 1.645, the amount that's going to be in the tail is equal to 0.05. Okay? And so 1.645 corresponds to the tail probability of 0.05, and it also corresponds to the number that we use, and you'll see at the bottom, for a 90% confidence interval, because for a 90% confidence interval, we want 5% in both of our tails. Okay, and then so if we look at, if we go further along, and I go to 0.025, that number shows up as 1.96, okay? And that means so this one's at 1.645, it says if I go out a little bit further to 1.96, then the area in this tail beyond 1.96 is 0.025. Is that good? So it's basically wherever you draw this number is you're going to have this much in the tail, 0.025 in the tail. Okay, so in our sample we had 30 men, okay? And if I want to make a 95% confidence interval, what is the number that I'm going to use?
0.025.
So with 30 men, how many degrees of freedom do I have?
0.15.
I have 29 degrees of freedom, and I'm going to go to the column 0.025, or the one that corresponds to 95% confidence, and that number 2.045, if I'm looking at this correctly.
How did you get the 29?
N minus 1.
N minus 1. I've got a sample of 30, so I'm going to do n minus 1 degrees of freedom. I have 29 degrees of freedom. And if I want to make a 95% confidence interval, I'm going to use this number, 2.045.
So
So my confidence interval
0.025.
So for 95, so with 29 degrees of freedom, a 95% confidence interval goes from y bar plus or minus 2.045 times my, I'm going to use the standard deviation from my sample S over the square root of n. Okay, so now it's just a matter of plugging in the numbers. And this becomes 69.7 plus or minus 2.045 times 3.1 divided by the square root of 30. Okay, so notice I'm still using 30 here. It's just 29 when I look up the degrees of freedom. So this becomes 69.7 plus or minus, and then I do the calculations. So I get 69.7 plus or minus 1.16. Alright, and so I get 70.86. And I get 68.54. Yes.
So just to clarify, everything on the right that comes after the plus and minus sign is going to be the adjusted standard deviation for this kind of problem?
Adjusted standard deviation.
Well, in other words, it seems like the 3.1 over root 30 is,
Yeah, so this is
the standard deviation.
This is the standard deviation of the sampling distribution.
Oh, I
Okay.
understand.
Yeah.
Okay.
That's the behavior of the y bar if we know where mu is. Okay. So it's actually sigma over the square root of n, but because we don't know sigma, we're going to use s as our best guess. But because s might not necessarily be correct, we compensate for that by using 2.045. So there's a few things going on there. Okay. It condenses down to this, but this is what's going on. Okay. And then I would write. I'm 95% confident what?
Mu.
Yeah, 95% confident that mu, which represents what?
The mean of the population.
Yeah, the mean height of all men in the United States is between 68.54 inches and 70.86 inches. Okay. Notice this is only a statement about mu, the mean height or the average height of a man in the United States. Okay. Of course, any individual male that I pick might not be in this range. Okay. But I'm 95% confident based on my sample of 30 men and getting an average of 69.7 and standard deviation of 3.1. Based on that, I'm 95% confident that the mean height of men is between there and there. Okay. So does this provide evidence that the mean height of men in the U.S. is not 70 inches?
No.
No, okay, because 70 inches is within my interval, so it's a plausible value, okay? On the other hand, 71 inches is not in my interval, so therefore I could say I have evidence that the mean height of men in the United States is not 71 inches, okay? Now, is it possible that the mean height of men is 71 inches?
Yeah.
Yeah, that's possible, but it would be surprising to us because it means that the sample of 30 that we took is was an extremely unusual sample in that it produced a mean of 69.7, which normally would happen very rarely because the mean, that 69.7, is supposed to come from a standard, supposed to come from a normal distribution. Okay, so it's possible that mu is actually 71, and we just happen to get this crazy sample that gave me a sample mean of 69.7. Okay, but I'm 95% confident that it's not. Okay, I'm 95% confident that the mean is between this value and this value. Okay, so in short, we do not have evidence that mu is not 70 inches, okay? It doesn't mean that mu is 70 inches, it just means we don't have evidence that it's not. On the other hand, we can say we do have evidence that mu is not 71 inches. Okay. So let's try, so in summary, okay, a confidence interval is in the form, or I should say confidence interval for mu, which is the only we'll make it another. Confidence interval for mu, meaning the population mean, is in the form y bar plus or minus t star, some critical value t, times s over the square root of n. Okay. And t star, this is our critical value. All of these parts have names, okay? S over the square root of n, this is our standard error. This term is our standard error. And y bar is our sample mean. Which also serves as our estimate of the population parameter. The t star times the square root of, t star times s over the square root of n. This is the entire plus or minus part. This is also known as the margin of error. Okay. And this makes an appearance when, not so much here, but when we're dealing with like during election season, they'll say so and so, candidate for mayor or whatever is polling at 51% with a 2% margin of error, okay? So if it's 51% with a 2% margin of error, that's like, you don't know if you're going to get a majority or not, right? Okay. All right. Okay. Now, in the book, you're going to have some homework where they're going to say, basically, if you want to, if you want your margin of error to be a certain value, how big of a sample do you need? Okay. That's just basic algebra, right? You set you say your margin of error is going to be less than some value, let's say 0.2 or whatever, okay? And basically you just back solve for n, okay, using your rules of algebra. Okay. And I think it's pretty straightforward in the book and homework. And you just basically guess a number for s here, okay? It feels a little arbitrary, but that's what you're doing there. Okay, let me do a little demo on the computer regarding confidence intervals. Okay.
I have a quick question.
Yes,
Can you just repeat what
please.
you said? If a question, when would we use this? If the question says what?
I don't know, margin of error? Or,
Yeah.
oh, if you want your margin of error to be a certain,
Oh.
within a certain percent, or a certain value, right? So, I mean, I could say I'm 100% confident that the average height of men is between, you know, is 69.7 inches plus or minus 50 inches, right? I could say I'm 100% confident that the average height of men in the United States is, you know, between 1 foot high and 12 feet high, okay? Now that's not a useful confidence interval because it's just so wide that we can't do much with it, right? If I gave that to a clothing company and I said, okay, give me a one-size-fits-all, they can't do anything with that, right? So you say, okay, well, if we want to make a one-size-fits-all, you know, we've got to figure out what the average is, and then we have to give ourselves some room for different. They don't ever say one-size-fits-all anymore. It always says one-size-fits-most now. And with car manufacturers, they wanted to, you know, try to make a car that fits everybody, that they can just ship globally. They couldn't do it. Okay, so if you go to like Asian countries, the cars will feel a lot smaller than the European and American cars because just from country to country, the sizes of people are different. Okay, that just happens. So, okay, let me just put a break in the video, and then we'll do something with the computer.